Welcome to The Explainer. Today we're looking at a highly practical computing technique that literally borrows its blueprint straight from nature. We're going to explore how we can take the principles of biological evolution and use them to solve massive, complicated logistical nightmares. We are talking about genetic algorithms. It's this absolutely fascinating way to blend the raw rules of nature with computer science, and by the end of this, you'll see exactly how the whole shebang works.
Okay, let's dive into this. Picture this. How do you find the absolute fastest route through thousands of cities? It's the classic traveling salesperson problem. Imagine a delivery driver needs to visit a whole set of locations exactly once and then return right back to the start, all while keeping the total distance as short as humanly possible. Sounds pretty simple, right? Well, mathematically, as you add more cities, the number of possible routes grows so incredibly fast that checking every single possibility, doing a brute force exhaustive search, becomes completely impossible. Even for a massive supercomputer, it would just take far too long. So we need a smarter, faster way to handle this.
To figure that out, here is our roadmap for today. We'll start with the routing problem, then ask what are genetic algorithms, look at survival of the fittest, crossover and mutation, real-world applications, and finally wrap up with strengths and limitations. Think of this as our journey from an impossible math problem all the way through the mechanics of simulated evolution.
Section 1. The routing problem. The traveling salesperson.
So optimization is a massive, absolutely crucial challenge for logistics companies today. Because the search space is overwhelmingly huge, we just can't solve it in one single perfect step. And that brings us to nature's blueprint as our surprise solution, the genetic algorithm. Basically, a genetic algorithm is a search and optimization technique. But notice the key phrasing here. It works with many candidate solutions at once, and it improves them over repeated generations. Instead of calculating a single perfect answer right from the start, a genetic algorithm searches for really strong solutions over time. It literally imitates biological evolution. Though thankfully, instead of taking millions of years, it runs in a matter of milliseconds.
Section 2. What are genetic algorithms? The search for good solutions. Section 3. Survival of the fittest, population and fitness. We're going to meticulously define the core mechanics driving the simulated evolution. Now here is where we really shift our focus from pure math over to biology. The fundamental motif we're looking at is the concept of good enough. We're not chasing perfection. The aim is to find a very good, highly efficient, approximate answer. And this brilliantly illustrates exactly how we map abstract biological terms directly to concrete travel routes. For those of you prepping for exams, definitely take note of this vocabulary. First, we have the population. In biology, that's a group of individuals, right? Well, in our algorithm, it's a set of candidate solutions, like different possible travel routes. Next up is the fitness function. That's just a measure of how good each solution is. In routing, a shorter route equals higher fitness. Finally, selection. Just like in nature, fitter individuals are more likely to pass on their traits. So here, we choose the strongest solutions, preferring those routes with the lowest total distance to form our next generation.
Section 4. Crossover and mutation. Creating new solutions, this is the actual engine of evolution.
Let's move to and see how this builds. Here is the actual loop of the algorithm. Step 1, we evaluate the fitness of our current solutions. Step 2, we select the stronger ones based on that fitness function we just talked about. Step 3 is crossover. This is where it gets fun. We combine parts of two selected parent solutions to create totally new offspring solutions. They inherit useful traits, or in our case, really good route segments from both parents. And step 4, we mutate them with small random changes. These stages just repeat, generation after generation, gradually improving the entire population.
Now pay attention to this part. Mutation introduces small, random changes so the search does not become too narrow or get stuck too early. Randomness is absolutely the secret ingredient here. If we rely only on selecting and crossing over the current best routes, we might actually get trapped in a decent solution while completely missing a much better one hidden somewhere else in the data. Mutation adds variety. It's the spark that prevents our simulated evolution from totally stagnating. Of course, evolution could theoretically go on forever, but let's be real, we need our delivery routes by tomorrow morning. So we introduce termination. This is simply the condition that stops the process, basically deciding that the search has gone far enough. We stop when the fitness is good enough, when the improvements between generations become incredibly tiny, or simply when a set number of generations has completed. It reiterates our core philosophy here. We are looking for a highly evolved, excellent approximation.
Section 5. Real-world applications. Moving beyond route planning. Let's zoom out a bit.
This algorithm is incredibly flexible. Anytime you have a massive search space where an exact, exhaustive search is just way too expensive, a genetic algorithm might literally be your best friend. For example, in scheduling, we can assign tasks, staff, or massive factory machines in a way that perfectly balances time, cost, and efficiency. In engineering, we can search for aerodynamic designs that meet strict constraints and performance goals. Or think about resource allocation, finding better ways to distribute limited resources across competing needs. Really, as long as you can clearly represent the problem and measure the quality of a solution, genetic algorithms can tackle it.
Section 6. Strengths and limitations. Evaluating the algorithm. This is critical for evaluating the approach.
So, the crucial point is understanding the balance here. On the strengths side, genetic algorithms effortlessly handle huge search spaces where a brute force mathematical search is entirely impractical. They find remarkably strong approximate solutions for very complex real-world tasks. However, looking at the limitations, you absolutely must remember that they generally do not guarantee the perfect, mathematically optimal solution. And perhaps most importantly, they heavily rely on a well-designed fitness function. If your evaluation criteria is poor, well, your simulated evolution will naturally produce poor solutions. It's kind of like garbage in, garbage out.
Which brings us to our final thought for today. If simulating biology can untangle the totally impossible logistics of global routing, what other massive, complex problems in our world are just waiting for a genetic algorithm to find the answer? It really makes you think, doesn't it? Thank you so much for joining me on this explainer. Keep exploring, and I'll see you next time.